Now we are going to be talking about threads in Java. Java threads are somewhat similar to POSIX threads. There are threads with higher priority, which are executed in preference to threads with lower priority, and one can set the priority of a thread. An interesting feature is that each thread can be marked as a daemon thread. We had seen so far the concept of daemon processes. Daemon threads are different. A daemon process, it's a process which runs in the background, having no terminal connection, and it's supposed to only interact with the user through the logs and through the network. Instead, the daemon's threads are threads which don't have to run in the background, but are threads that are not essential for the execution of the program. And the idea is that if all the remaining threads of a program are marked as daemons, so all the non-daemon threads finished, then the Java virtual machine can just terminate without any further computation. So service threads running in the background, which only help with the graphical user interface, can, after the graphical user interface terminates, they can be terminated without any additional care. Whenever one thread is created, it inherits the property of its parents, like its priority and its state of being or not being a daemon thread. Let's see how you create threads in Java. On the two columns in this slide, you see two different solutions. The first one is based on extending the thread class over here, and the second one is based on implementing runnable. Which method should one select? Well, if your class has to extend a different class, and since in Java one is allowed to extend a single class, then the only available solution will be to implement runnable. Otherwise, extending a thread, it's just minorly more comfortable. So let's see the difference between the two. In both solutions, the class that extends threads or that implements runnable will have its local variable, will have a constructor initializing them, and a run class, a run method. The run method is the main method of the thread being executed, the equivalent with the functor in the function operator in C++. Then the main difference between the two implementations lays into the way the thread is started. With the extension of a thread, the way to start a new thread is to create an object of the thread class, of the class that extends the thread class, and then call start on it. With a method implementing runnable, one has to create a new thread. In the constructor of the thread, one gives as parameter an instantiation of the object implementing our new class that implements runnable, and start is called on the thread created in this way. So this is the only difference. with implementing Gradable, one has to create a thread that encapsulates the class that has been defined. In order to communicate between threads in Java, there exists a mechanism a little bit similar with the mutex. However, Java being an object-oriented class, we do not have the procedural approach of entering a region and exiting a region, but rather the region is a block, and the block of code that is in the region where threads are mutually exclusive is marked with the synchronized keyword, so synchronized of the object, where O can be any object in the system. The behavior is that whenever a thread of execution arrives and enters this block, no other thread can enter this block of data from the opening parenthesis of the synchronized to the ending parenthesis of the synchronized, except if the thread holding the area, the thread currently executing inside this block, calls object wait. In order to wake up an object that is waiting, other objects can meanwhile enter the block, only one at a time, and they can wake up the object waiting on his condition. Notice that here the wait on the object on which the system is synchronized, it's equivalent with waiting on a condition variable in C with mutexes. And we have the methods object notify and object notify all, equivalent of broadcasts, that can wake up one or all objects that are currently blocked on some condition inside this mutual exclusion area. What you should note here is that the notify and the wait have to be inside the synchronous blocks. The reason is, according to the designers of the mechanism, to make sure that programmers achieve predictable behaviors, right? When one calls notify or broadcast outside a mutual exclusion in C, sometimes that works, but some other times the system may lead to deadlocks in case the notify is lost just before the internal thread is going to sleep. It is up to the programmer to know whether calling notify and broadcast in C it's okay outside of mutual exclusion area, but if the programmer is not very careful, then this can lead to deadlocks, difficult to debug. So in Java, this condition is avoided, this possible trouble is avoided. Nevertheless, there are situations when forcing the programmer to enter the mutual exclusion area in order to send a notify may decrease the efficiency of the program. Since there may be nobody to wake up, or the mutual exclusion area is now occupied by a thread that is not sleeping, not waiting on any condition, so just to send the notify that nobody needs, your thread that sends the notify will be blocked for a while, waiting to enter the mutual exclusion area. An example of where this kind of drawback is manifested is if you consider the synchronized counter, like one that increments 1, 2, 3 and so on. And you have two types of threads. The threads of type 1 act only when the counter is even, and the threads of type 2, there can be multiple of them, can act only when the counter is a multiple of 3, let's say. This is not a little bit unlike the implementation of the Fibonacci that we have discussed at C threads. Now, an implementation of such a system based on a mutual exclusion in C is generally can be more efficient than one with a synchronized object in Java. In C, you can have two types of condition objects, one for even values and one for multiples of 3, while in Java, with a single object, you can have a single condition variable, and one would have to notify all the threads, even if those that are not expected to run at the current moment, to wake them up, generating executions that are not desired or that slow down the system. See pthread condition broadcast for more information about what the behavior is in C. In summary, if we contrast C and Java signaling between threads, we notice that Java uses the same object for signaling, and it uses the same object also for implementations of mutex and the condition variable, which means there's a shorter effort for initialization than in C, where you have to initialize condition variables and mutual exclusion variables. On the other side, C is more flexible, allows several condition variables for one mutex, allowing therefore a much higher selectivity in delivering signals. C has additional libraries and mechanisms. One of the most important, besides mutual exclusions, are semaphores. A semaphore is a variable whose positive value tells how many threads are waiting for the semaphore to be freed. And the semaphore is incremented synchronously. A semaphore is initialized with semaphore init and closed with semaphore destroy. It's a resource of the system, so one has to destroy them to let the system know that the new resources are available. In order to increment the semaphore, one calls semaphore wait. If the semaphore value was already positive, then the thread is put to sleep. To not be put to sleep, one can call try wait, which is non-blocking and returns with an error message if the area was not accessible. And semaphore get value, it's telling the current value of the semaphore. In order to let other threads enter the area, the thread that exits, it's going to call semaphore post. In order to suspend a thread, it was that's one of the important problems. If, for example, a program needs to exit and it would like to close cleanly all the threads that are still running, it was noticed that an important problem there is that threads may be holding resources such as semaphores that have to be correctly cleaned before exiting. So just killing a thread in the middle of its execution, it's in general unsafe. The current recommended techniques with Java involve waiting and notifying. So this is an implementation recommended. You would have a thread that it's waiting for somebody to wake it up, and it's going to call sleep, and while it's not suspended, it's going to wait. Then if it's suspended, it's just going to get out of the while loop and continue repainting. Otherwise, if the thread is suspending, it will just keep staying in the wait condition. In case an interrupt is raised, then the interrupt will be propagated. There's an important difference between cancellation of threads with POSIX and with Java. The simplest cancellation mode in POSIX is pthread cancellation deferred. This is the recommended version where threads can be requested to terminate, but they will not terminate immediately. Instead, the threads that are cancelled are going to test at certain safe points where they are requested to exit, and will exit only in those safe points where all the resources are cleaned. Asking a thread to terminate is done with pthread cancel. Another mechanism of exiting is with the pthread cancel asynchronous mode, which would allow to terminate a thread at any moment. However, in order for that to be done correctly, one has to register callbacks. The callbacks are based on stack of functions that have to be executed in order to clean resources at the moment of an asynchronous cancellation. So one can push functions that clean semaphores and free memory, and one can pop the functions cleaning the resources whenever those resources are cleaned themselves by the thread naturally. In order to handle deferred cancellation, in moments of safe cancellation are marked by a thread calling pthread test cancel function that does not return in case cancellation was requested. Another point of cancellation is whenever a wait on a condition variable happens. In Java, instead, cancellation cannot be done from outside of a thread. One can just tell the thread to terminate using a shared variable. So an external method can call thread interrupt, which will interrupt the thread, but the thread will have to check its exceptions, see that it was requested to interrupt, and at that moment the thread can check it with is interrupted, and at that moment the thread can clean its resources and prepare to exit. A thread that calls interrupt in order to cancel another thread would typically also clean all references to the thread that it's been cancelled, and can wait for the dying thread with thread join. A thread that no longer wants to use a CPU in the detriment of other threads can call thread yield to give other threads a chance to execute before going further. This is a way to implement nice threads, which will allow the rest of the threads on the system to execute while they are performing heavy computations. This was particularly important with green threads, for example, which require the mechanism to let the scheduling thread to start other threads. Java organizes threads in thread groups. This was important, especially to allow execution in sandbox of untrusted code. So whenever untrusted code, like an applet, it's launched, a thread group can be created with limited rights set by the parents. A thread cannot control threads in its parent group. And but this was one of the important features that enabled security for applets. Except for a few bugs here and there. Thread pools are an important concept for supporting concurrent servers. In order to implement a concurrent server using a thread pool, namely class that enables and manages a limited number of threads to avoid new threads creation and termination each time a client connects. One can use this class over here, the executor service. So in such a server, one would initialize the server socket and the pool with a predefined pool size, a number of threads we want to have in our thread pool. And then each time a new client connects on the server socket, we would create a handler that encapsulates and can execute the thread serving the client, and the pool would be requested to provide a thread to carry to execution our handler, which implements runnable. This is performed with a pool execute function method. At the end, whenever an exception occurs or for some other reasons the server is terminating, then pool shutdown, it's called to terminate the server. If one wants to terminate the pool from outside, the mechanism is to first stop new threads from creation. This is done with pool shutdown. And now if you want to also terminate threads that are currently executing, then the mechanism is based on await termination, which can give them a certain timeout, like here, 60 seconds, after which they can be requested to shut down now. Some threads may still linger despite the urgent request to shut down, and if some threads are just not getting out, then a new after a new deadline, then the termination can be forced by just exiting from the func method. Next, we are going to be talking about mechanisms to synchronize threads or to manage threads in ways that can be proven theoretically to be correct. There are such mechanisms which allows the management of applications with large number of threads in ways that can be proven for correctness, like active objects, Petri nets, and so on. However, for most complex systems, you have to be aware that it is actually impractical to use any of those. Nevertheless, the mechanisms enabled by those approaches can help the design of systems with architectures that can be proven, at least on paper, if not automatically.